Hello everyone, this is my second session of the topic data structures. In the last session, I had covered introduction, types of data structures as well as operations on data structures. In this session, I am going to start with arrays, types of array and memory representation of array. Let us see need of the array. Suppose I am declaring a variable using any one of the primitive data type and storing a value in it. That is int b is equal to 5. Now, if I need to store another value, then either I have to declare another variable or I have to store the value in the same variable itself. But here the problem is, if I go on and declare new variables, then the complexity of the program increases. But if I store the value in the same variable, then the old value will get replaced with the new value. In this condition, I need a variable that can hold a set of values, that is called as an array. How we can define an array now? Array is a finite collection of homogeneous elements under same data type and under the same name. What array contains? It contains a set of homogeneous, that is similar type of elements, and they should be declared under same data type and they will be having the same name. That is, if I declare an integer array, then I can store only integer elements, not character or floating point numbers. Let us see some more details about array here. Every item stored in an array is called as element of that array. All the elements of an array are stored in continuous memory locations. Each item of an array can be accessed by a numerical value which is called as an index or subscript of that array, and it starts from 0 and ends up to n minus 1, where n represents the number of elements in that array. Array can be declared in various dimensions. According to that, arrays are classified into three types: one-dimensional array, two-dimensional array, and multi-dimensional array. An array with only one subscript is called as one-dimensional array. See the declaration here: data type, array name, size. This declaration is very similar to the normal variable declaration, with the only difference that is we need to provide size, which tells the number of elements that can be stored in that array. Let us see one example regarding this. Int a of 5. Here I have declared an integer array named a that contains 5 elements. After declaring an array, we need to store some values for further processing. This can be done in two ways: during compile time and during runtime. During compile time, the values of the array are provided at the time of declaration itself. Example, int a of 5 is equal to, the values should be provided within the flower braces. Runtime initialization is used for large arrays or to initialize an array with user specific values. See the example here. An array of 5 elements is declared. For loop is used to provide the values one at a time. This for loop repeats for 5 times since the size of the array is 5 here. Once the array is declared and initialized, all the elements are stored in successive memory locations. Consider an example. Here, an array of 5 elements is declared and initialized with values 1, 2, 4, 8, and 16. Memory representation of this array can be shown in the diagram. Each element of the array is associated with array name and a unique index value which starts from 0 up to array size minus 1. Using this, we can access any element of the array. That is, if I want to access 1, then it is referred to as a of 0. If I want to access 4, then it is referred to as a of 2. Similarly, each block of memory will be having a memory address. Suppose this block of memory starts with the address 100. This is called as the base address because it is the address of the first element of the array. The addresses of next elements can be easily calculated as this is an integer array and each element occupies 2 bytes of memory. So now the address of 2 will be 102, 4 will be 104, 8 will be 106 and 16 will be 108. In general, memory addresses of any element I can be found by using the formula a of I is equal to base address plus number of bytes occupied by the element into index of the element. Applying this formula with the same example, suppose if I want to find the address of a of 2, then 100 plus 2 into 2, that is base address plus number of bytes into index of the element, we get 104. Now coming to two-dimensional array, it is an array which contains two subscripts: declaration, data type, array name, row, column. See the example: int a of 3 3. Elements of two-dimensional array are stored in the form of matrix. So we need to specify number of rows and number of columns while declaration. In this example, array named A contains 3 rows and 3 columns. That is, it is having 3 into 3, that is a total of 9 elements. 2D arrays can be initialized by using one of the two ways: compile time and runtime. During compile time, all the elements are provided within the flower braces at the time of declaration. During runtime, elements are entered at the time of execution by using for loop. In case of two-dimensional array, we require two for loops, that is one for row and another one for column. Consider the same example, int a of 3 3. This array is having 9 elements and all the elements are stored in a matrix form. Each element can be accessed by using array name along with the two subscripts. Each of the subscript will be having index value which starts from 0 up to row or column size minus 1. So if I want to access the element 5, then it is referred to as a of 1 1. Similarly, if I want to access the element 9, then it is referred to as a of 2 and 2. Elements of 2D array are stored in continuous memory locations. It can be represented in memory in one of the two ways, that is row major order and column major order. In row major order, all the elements are stored row wise. See the example here. The array contains 3 rows and 3 columns. First row elements will be stored in first 3 consecutive locations. Second row elements are stored in next 3 consecutive locations, and similarly the last row elements are stored in the last 3 consecutive locations. The memory address of any element A of ij in a 2D array can be found by using the following formula, that is A of ij is equal to base address plus W of n into I minus LB plus j minus LB, where base is the address of first element of the array, W is the number of words per memory location. The value of W depends on data type of the array. N is the number of columns. I and J are the indices for row and column. LB is the lower bound. In column major order, elements are stored column wise. See the example here. First column elements are stored in first 3 consecutive elements. Second column elements are stored in next 3 consecutive elements, and so on. Memory address of any element A of ij in column major order can be found by using the formula A of ij is equal to base plus W of I minus LB plus M into J minus LB, where base is the address of the first element of the array. W is the number of words per memory location. M is the row. LB is the lower bound. I and J are the indices for row and column respectively. Let us see one simple problem regarding this. Consider the array A of order 25 into 4 with base value of 2000 and 1 word per memory location. Find the address of A of 1213 in row major order and column major order. How to solve this? Just write down all the given elements. Base address is 2000. Number of rows, that is m, value of m is 25. Value of n, that is number of column, is 4. Lower bound is always 0 as the index value starts from 0. W, that is number of words per memory location, is 1. I value is 12. J value is 13. So in row major order, substitute all the elements in the formula. The answer we will get is 2061. Similarly, in column major order, substitute all the values in the formula. The answer is 2337.